Okay, we're looking at 7.2c today. The first question says, a report on the National Center for Health Statistics says that the heights of 20-year-old men have mean 176.8 centimeters and standard deviation 7.2 centimeters. There are 2.54 centimeters in an inch. What are the mean and standard deviation in inches? So we're doing a conversion here, a transformation, and the transformation from centimeters to inches is that we are going to need to divide by 2.54. So to get the mean in inches, we take the original mean and divide by 2.54. That's just a straight multiplication by a factor, and that gives us 69.606 inches. And to find the standard deviation in inches, we're using the formula from your notes. It's formula number 1 from the rules for variances section. And that formula uses variance, so it uses sigma squared, but obviously we're doing standard deviation, so we need to take the square root of each side. That's why I've got a square root symbol over here. But that formula says that we do b squared times the original standard deviation squared. And our b, again, was dividing by 2.54, so we have 1 over 2.54. We square that, we multiply by the original standard deviation, 7.2 squared, and take the square root of our answer, and we get 2.835 inches. Question 2 says that you have 2 instruments with which to measure the height of a tower. If the true height is 100 meters, measurements with the first instrument vary with mean 100 meters and standard deviation 1.2 meters. Measurements with the second instrument vary with mean 100 meters and standard deviation 0.85 meter. You make one measurement with each instrument. Your results are x1 for the first and x2 for the second, and each of these are independent. So part A wants to know if we combine the 2 measurements, we could do that by averaging. And so the average that they say is x1 plus x2 over 2, and we're going to call it y, is our new calculation. They want to know the mean and standard deviation of y. So to find the mean, again, like they said, we're going to average the means of the original, so mu of x1 plus mu of x2, divide each by 2. So essentially that is going to give half of the weight to each of the means. So half of the first mean and half of the second mean. So we're taking half of the first mean was 100 and the second mean was 100. So each of these half of 100, you add them, you're going to get 100. That's a pretty easy part. The standard deviation for y is a little bit trickier. Again, we're going back to that first equation from the rules for variances, where we're doing b squared times the original standard deviation squared. But this time, because our original standard deviation is now a sum of 2 things, we need to add these 2 values together. Our b value from up here was still a half. That's our conversion factor. So we're doing a half squared times, and then the first standard deviation is 1.2, and we're squaring it, plus the second standard deviation was 0.85, and we're squaring that. When you just dump all this information in your calculator and you take the square root, you're going to get 0.735. So part B says that it makes sense to give more weight to the less variable measurement because it is more likely to be close to the truth. So conceptually, that means if we go back and look at the 2 standard deviations, we want to give more weight to the number that's closer to 1. Or actually not closer to 1, just closer to 0. So, because obviously a standard deviation of 0 would mean that there's no variation at all. So this second one, 0.85 meters, is closer to 0 than the first one. So we're going to give more weight to the 0.85 meters than we are to the 1.2 meters. So we're giving more weight to the second measurement instrument than the first measurement instrument. And the way we're going to do that, it says that statistical theory says that to make the standard deviation as small as possible, you should weight the 2 measurements inversely proportional. Inversely means like the reciprocal, inversely proportional to their variances. So we need to look at the variances of each of these measurements. And they tell us that since the standard deviation of the first is 1.2, to find the variance, we would square that. When we square 1.2, you're going to get 1.44. And when we square 0.85, we get 0.72. And so the first standard deviation, or the first variance, is about twice as big as the variance of the second one. So we want to do the inverse relationship of that. So if this variance is half as big as this one, we need to weight this twice as much as this one. So if you're weighting this twice as much and this as one time and twice as much, 1 plus 2 gives you 3. So the second measurement is 2/3 of the weight and the first measurement is 1/3. So you can see 2/3 is twice as big as 1/3. So we're giving this twice the weight of this because this variance for x2 was half as big as the variance from x1. So that explains how we get this equation. And now we're going to find the mean and standard deviation of W. So the mean of W would be 1/3 times the mean of the original one. And the original mean, remember, for each of these was 100. So we're doing 1/3 of 100 plus 2/3 of 100, which again is just going to come out to 100. And our standard deviation for W, what we're going to do is, again, take the square root of the 1/3, the B value. For our first one, it's B is 1/3. We're doing that squared times the original standard deviation squared, plus 2/3, our B value for the second measurement, squared times 0.85 squared. When you put this whole expression in your calculator, you're going to get 0.481. You take the square root and you will get 0.694. So the standard deviation of W is 0.694. So you can see here that individually, the first measurement had a standard deviation of 1.2. The second one had a measurement of 0.85. If we just average these two, we get a standard deviation of 0.735. So it's smaller, it's better than each of the two that we were given originally. But if we optimize the standard deviation through this statistical theory setup, we get an even smaller, right here, we get an even smaller standard deviation. 0.694 obviously is the smallest standard deviation possible that we've seen so far. So the goal here, what they're saying is that when you do any calculations, it's best to make the standard deviation as small as possible, and this is the way that we do that. So that's the whole practice quiz for 7.2.